An eruption from the sun was sort of like a solar tsunami, traveled out to where Voyager is today, some 18 billion kilometers away.
NASA's Voyager 1 continues to astound the globe with astounding discoveries after 45 amazing years of space travel. Launched in 1977 to investigate the outer planets, this fabled spacecraft has traveled farther than any other man-made object in history. A Nobel laureate recently disclosed that it is returning data that scientists never believed was feasible. Is this the secret to solving deep space's biggest mysteries? Exploiting an alignment that only occurs once every 176 years. The Voyager mission's exploitation of an extraordinary planetary alignment is among their most intriguing features. The speed at which planets orbit the sun varies, and most of the time, their alignment prevents a single spaceship from visiting several worlds with ease. In the late 1970s and early 1980s, however, engineers found that Jupiter, Saturn, Uranus, and Neptune would be positioned in such a way that a single spacecraft could jump from one planet to the next with the help of a meticulously planned sequence of gravity aids. The Grand Tour was the name given to this possibility. Early in the 1970s, it had come up in NASA planning circles, but there were questions about its viability due to issues with cost, complexity, and the maturity of the technology. There could be as many as 4 or 5 planetary contacts on a full grand voyage. Although the initial plans were complex and called for multiple spacecraft to manage various encounters, project management ultimately refined the idea into the 2-spacecraft Voyager mission. Though more practical considering the resources and technology at hand, this was nonetheless state-of-the-art. Because the spaceship would receive a free speed boost from each gravitational slingshot, the alignment was essential. In the absence of these aids, the mission would have needed an unfeasible rocket and enormous volumes of fuel, which would have made the launches very costly or perhaps impossible. Each Voyager could conduct a series of planetary flybys, collect data, and then point itself at the next planet if the launches were timed to correspond with the alignment. The path was slightly modified by an occasional little engine burn to meet each new target at the exact distance and angle. Despite the fact that Voyager 2 was launched on August 20th, 1977, Voyager 1 was launched on September 5th, 1977, and because to its shorter and faster trajectory, it reached Jupiter first. People who believe the numbering should correspond to the order of launches are occasionally confused by the choice to call them 1 and 2, which was more about mission objectives than launch dates. NASA, however, desired that Voyager 1 follow a course that would allow for the most thorough examination of Jupiter and Saturn, particularly Titan, Saturn's largest moon. Meanwhile, Voyager 2 was able to go to Uranus and Neptune because of its somewhat slower path, assuming all went smoothly. The entire potential of this chain of gravity assistance required meticulous tracking, meticulous timing, and hundreds of calculations. The angles were calculated with amazing accuracy by teams at NASA's Jet Propulsion Laboratory. Since each spaceship covered tens of millions of kilometers nearly every month, even a small navigational mistake at any point could have disrupted the entire itinerary. Thankfully, both spacecraft remained on course with unexpected accuracy. Using radio signals, NASA's base stations, collectively referred to as the Deep Space Network, tracked each probe and provided course adjustments as necessary. In just over 10 years, NASA was able to collect a lifetime of planetary science thanks to this alignment, which is extremely uncommon in cosmic terms. Additionally, it put Voyager 1 on a course that would eventually propel it well above the planet's plane and into interstellar space. The alignment made it possible for Voyager 2 to visit Uranus in 1986 and Neptune in 1989, making it the first and only spacecraft to do so. The alignment had fulfilled its primary function when the flybys were completed and the spacecraft were launched on an escaping trajectory away from the Sun. These 2 spacecraft alone achieved one of the most remarkable exploration accomplishments in history, despite the Grand Tour concept being reduced from its original multi-probe plan. This was made possible by a cosmic coincidence that will not occur again for a very long time. inventive instruments in spacecraft design, built to function far from the sun and gather as much scientific data as possible about the places they traverse. Voyager 1 and Voyager 2 have almost identical architecture, with multiple instrument booms stretching outward and a big dish antenna on one side. Each spacecraft is about the size of a compact car. Images of the Voyagers are so familiar that they frequently show up in science features, documentaries, and even pop culture references, making sure the spacecraft could endure for years in the frigid and radiation-rich depths of space was one of the main design problems. Strong gravitational fields and dense fields of charged particles could be dangerous during frequent planetary flybys. Therefore, they needed to be resilient enough. Instruments including cameras, magnetometers, plasma detectors, cosmic ray detectors, and others are used to study each Voyager. These instruments recorded amazing images and measurements of planets and moons early in the voyage, although some cameras and instruments were eventually turned off to conserve power over time. A core set of sensors continues to collect data today. Onboard computers, command and data systems, fuel tanks, and other parts are housed on a main bus that forms the core of the spacecraft structure. The big high-gain antenna, which is essential for communications, is connected to this bus. To transmit data, this antenna must always be pointing toward Earth. Signals can now take more than 20 hours to travel one way because the journeys are now billions of kilometers afar, and each year that time increases. The Voyager spacecraft are powered by radioisotope thermoelectric generators, RTGs, in contrast to many other missions that employ solar panels. At Jupiter's distance and beyond, solar energy is insufficient to adequately power spacecraft equipment. In contrast, RTGs produce power using the heat produced by plutonium-238's natural disintegration. Because of its architecture, the spacecraft has been able to continue operating even in the darkest regions of interstellar space and the outer solar system. It's amazing that both spacecraft can still interact with Earth on a regular basis, even though the power does gradually decrease over time, and NASA must limit which sensors remain operational. Additionally, each Voyager has thrusters and gyroscopes for controlling attitude. The spaceship maintains its sharp end in this way. The Earth-facing dish antenna and how they make small adjustments to their orientation to control their instruments. NASA's Deep Space Network, a collection of antenna sites located in California, Spain, and Australia, facilitates communication. Over the decades, NASA improved reception equipment to ensure that the weak signals could still be detected, pass the data, and be interpreted as the spaceship got farther away. An interesting aspect of Voyager design is the renowned golden record, which is mounted on the side of each craft. It is a 12-inch gold-plated copper disc with sounds and pictures chosen to illustrate the diversity of life on Earth, but it is not a scientific instrument in the traditional sense. Numerous languages have been used for greetings, a variety of musical compositions from other cultures, and even encoded visuals showing the whereabouts of our solar system, flora, animals, and human communities. The content was selected for the record by Carl Shawn and others in the hopes that, should any extraterrestrial intelligence ever discover it, it would act as a cosmic greeting. NASA built this spacecraft with dependability in challenging environments in mind. Although it paid off, this careful approach occasionally resulted in some elements being heavier or simpler than the state-of-the-art electronics of the time. Voyager's robust design, which regulates power distribution and voltage levels, helps to explain why they have been in operation for so long. Even when the available power gradually decreases, engineers have managed to keep the essential instruments operating. The spacecraft's ability to continue operating this much over their intended mission lifetimes is evidence of the sound design techniques employed in the 1970s. Not to mention that the Voyagers have backup systems for important tasks. For example, in the event that the primary thrusters or computers fail, they can switch to backups. They have been able to withstand sporadic malfunctions and continue to function thanks to this redundancy. The spacecraft's onboard software has been upgraded by ground controllers over time, forcing them to adjust to shifting conditions and new mission phases. Decades after their launch, the Voyagers continue to stand as two of the best examples of spacecraft durability and ongoing scientific return because of their flexible design and strong engineering, surviving in the dark and using radioisotope power systems. Choosing how to power the spacecraft is one of the main challenges in developing missions to the outer solar system. Satellites in the vicinity of Earth can be powered by solar panels. With solar panels suited for the weaker sunlight, solar energy can even power journeys to Mars or the asteroid belt. However, sunlight gets so dimmer outside of Jupiter's orbit that big solar panels are no longer feasible. RTGs, which turn heat from the decay of the radioactive element plutonium-238 into energy, are used by both Voyager spacecraft. Electric generators powered by radioisotopes are not a novel technology. Some previous missions, such as the HALV, Apollo Luna surface experiment packages and the Pioneer probes, used them. However, because the vessel required to be reliable for years, if not decades, Voyager's usage of RTGs was particularly crucial. Initially, the RTGs provide a few hundred W of electricity per spacecraft, which progressively decreases over time. Although that may not seem like much electricity, less than a standard light bulb in the house is sufficient to power the computers, telephones, heaters that keep the spaceship systems from freezing, and the main instruments. Safety is a priority in the design of RTGs. To lessen the possibility of radioactive particles being scattered in the case of a launch accident, plutonium-238 is encapsulated and in ceramic form. Luckily, neither of the Voyager launches failed, so these safety measures were put to the test. Once in space, a continual flow of electricity is guaranteed by the radioactive material's constant temperature in order to power the spacecraft's internal systems and take photographs and measurements during planetary flybys, even while they were operating several astronomical units from the Sun. This was essential. The power output decreases over time as the internal components age and the plutonium decays. By carefully arranging instrument usage and hibernating specific subsystems, mission planners must determine which instruments to stay alive. The Voyagers are still able to transmit back data because engineers have been able to save enough power. But eventually, the RTGS won't generate enough power to maintain the antenna's appropriate alignment or power any equipment. According to scientists, this could occur in the late 2020s or early 2030s. However, how well the spaceship itself holds up and how the generators deteriorate will determine the exact timeline. Every available power is carefully distributed to prolong spaceship life till that time. Small amounts of power are needed by attitude control systems to maintain thruster operation and heat the hydrogen fuel lines. Power is also necessary for communication. Sending a powerful enough signal back to Earth uses a lot of spacecraft power, whereas receiving commands from Earth doesn't. In order to conserve energy, cameras and high-resolution imaging devices that required more heated enclosures and data bandwidth had to be turned down gradually. These days, devices that measure charged particles, cosmic rays, and magnetic fields provide the majority of scientific findings. Great resources for learning about interstellar space. None of these would have been feasible without RTGs. The meager amount of sunlight provided by the outer solar system's darkness is insufficient for conventional solar arrays. In the 1970s, any viable solar systems would have been massive, heavy, and probably too brittle to last for decades in extreme environments. RTGs are dependable, portable, and long-lasting. Because of these factors, the Voyager missions serve as a paradigm for conducting operations well beyond of our planetary neighborhood. The encounter with Jupiter. The first major destination for both Voyager spacecraft was Jupiter. With a diameter more than 11 times that of Earth, this enormous gas giant is the biggest planet in our solar system. The opportunity to test the craft's equipment and learn more about Jupiter's atmosphere, moons, rings, and severe radiation belts was abundant when visiting a planet of such type. It was predicted that Jupiter would be full of surprises by the time the Voyagers arrived. Although they had made a brief visit in the early 1970s, Pioneer spacecraft had fewer instrumentation. The closest approaches to Jupiter were achieved by Voyager 1 in March 1979 and Voyager 2 in July 1979. The strong volcanic activity on Io, one of Jupiter's several moons, was one of the most important findings made during these encounters. Observations revealed that several active volcanoes were ejecting sulfur-rich plumes high above the surface of Io. Scientists were taken aback by this since they had not anticipated such geological activity so far from the Sun. This finding demonstrated that the interior of a moon might be drastically heated and reshaped by the tidal pressures of a massive planet. A secret water ocean beneath its icy crust is an intriguing target for future study, as evidenced by Europa, another moon with fewer visible craters and a smooth ice-covered surface. Additionally, Voyager's findings sharpened our understanding of Jupiter's atmosphere. The Great Red Spot, a massive storm bigger than Earth that has probably been raging for a century, was captured in stunning photos by the spacecraft. The data revealed lightning in the atmosphere, strong winds, and whirling cloud patterns. Scientists discovered that ammonia crystals are a component of the vivid, colorful patterns found in the various layers of Jupiter's cloud tops. Each Voyager also discovered indications of a weak ring system surrounding Jupiter. Saturn had rings before this, but it wasn't until the Voyager flybys that Jupiter's rings were properly discovered. The discovery was another surprise that altered our understanding of the outer planets, Titan and Saturn, even though Jupiter's rings are much fainter and smaller than Saturn's. For millennia, people have been fascinated with Saturn due to its beautiful ring system. The rings of Saturn can be seen as a remarkable spectacle even through low-powered telescopes on Earth. The rings of Saturn had only been observed from a distance by astronomers prior to the Voyager missions. Furthermore, although Pioneer 11 had provided some useful information, it was far less thorough than what Voyager could accomplish. Late in 1980, Voyager 1 made it to Saturn, and in 1981, Voyager 2 did the same. Expectations were exceeded by what the Voyagers found at Saturn. Numerous high-resolution photos of the rings captured by the spacecraft showed that they were composed of innumerable tiny particles, some as little as sand grains and others as big as rocks. The rings had intricate structure with thin ringlets, gaps, spokes, and waves rather than being merely a few wide, homogeneous bands. This new information implied gravitational interactions between Saturn's larger moons, small embedded moons, and ring particles. These so-called shepherd moons were identified by scientists as contributing to the preservation of rings' sharp edges. The in-depth examination of Titan, Saturn's biggest moon, was another highlight. Titan has a large atmosphere and is larger than the planet Mercury. Scientists were particularly interested in Titan's thick, hazy air, which is high in nitrogen and organic compounds, as Voyager 1 passed by. Unfortunately, the haze was so thick that the surface was not directly visible to visible light cameras, but the findings suggested that Titan might have oceans or lakes composed of ethane or methane. When liquid hydrocarbon lakes were proven by subsequent missions like Cassini-Huygens, this conjecture proved to be accurate. Titan's dense atmosphere and chemical chemistry made it one of the solar system's most fascinating moons in no time. It is compared to early Earth by some scientists. There were surprises among Saturn's other moons as well. For the first time, Mimas was photographed in detail, revealing its enormous Herschel crater, which gives the moon a resemblance to the Death Star. The highly shiny appearance of Enceladus suggested a dazzling icy surface. Later expeditions would reveal this, even if Voyager did not discover its geysers. Additionally, by observing a range of surface characteristics on moons such as Tethys, Dione, and Rhea, the Voyagers advanced our knowledge of the evolution of ice satellites. Mission controllers also had to make some difficult decisions during this time. To gain a better look at Titan, Voyager 1 changed its course after Saturn. Thus, it was unable to proceed to Neptune or Uranus. On the other hand, Voyager 2 passed Titan farther away while maintaining a course that would enable it to visit Uranus and Neptune after Saturn. Nevertheless, both spacecraft achieved their goals at Saturn, obtaining photographs and data that changed the course of knowledge about moon geology, ring physics, and the environment of a gas giant. The sole trips to Neptune and Uranus. Voyager 2 holds the unique status of being the only spacecraft to make close-up visits to Uranus and Neptune. These far-off ice giants have never been visited by any previous spacecraft. Because of this, the information collected continues to represent our greatest direct observations of these planets to date. Scientists were both thrilled and uncertain about what to anticipate when Voyager 2 landed on Uranus in January 1986. The axial tilt of Uranus makes it an odd planet. It appears to be rolling on its side around the Sun due to a 98 degrees tilt in its rotation axis. Voyager 2 discovered during the flyby that Uranus has a more intricate ring structure than previously thought, despite the rings appearing less extensive and darker than Saturn's. 10 new moons were also found. Miranda, the huge moon, has one of the strangest surfaces in the solar system according to the mission's cameras, characterized by scarps, patchwork terrains, and canyons that allude to a turbulent geological past. The magnetic field of Uranus does not align with the planet's rotational axis, which was another unexpected finding. The fact that the center of the field is out of alignment with the planet's core suggests that something strange is occurring deep within. Voyager 2 proceeded to Neptune after Uranus, arriving in August 1989 to this far-off world. The dynamic environment of Neptune was surprising. At high latitudes, scientists observed rapidly moving bright clouds and a large dark patch that resembled Jupiter's Great Red Patch. Neptune contains rings, just like Uranus, although they are weak and unfinished. It was discovered that Triton, the planet's largest moon, had an active geyser of nitrogen gas or nitrogen-laden debris erupting from its surface, as well as a thin nitrogen atmosphere. Triton was probably caught at some point in the distant past because it orbits Neptune in the opposite direction of the planet's rotation. Jupiter and Saturn are frequently given more attention than Uranus and Neptune. However, the results of Voyager 2 showed that they are intriguing fields in and of themselves. The results from the spacecraft raised fresh questions regarding the formation of these worlds and assisted researchers in improving models of the compositions of ice giants. For example, the fact that their innards include water, ammonia, and methane ices points to a different evolutionary trajectory than that of Jupiter and Saturn. Additionally, the results suggested that these planets may have water layers deep down that could affect their peculiar magnetic fields. One of Voyager 2's greatest accomplishments during the original mission was its successful flyby of Neptune. It sped off toward the outer limits of the solar system after the collision in August 1989. Voyager 2 exceeded NASA's expectations by visiting 4 outer planets, numerous ring systems, and dozens of moons. In the meantime, Voyager 1 had already departed from the planets after Saturn's playing and was on its way to interstellar space. Together, they continue to serve as a testament to how a carefully thought-out mission can take use of a special orbital opportunity to collect vast amounts of data. Beyond the heliosphere. Beyond Neptune, the planets give place to a region of tiny icy bodies called the Kuiper Belt. The hypothetical odd cloud, a cometary reservoir that would stretch almost halfway to the closest stars, is even farther away. However, the outer edge of the heliosphere, where the solar wind interacts with the interstellar medium, is one of the next frontiers after Neptune. There are several zones along this boundary, rather than just one line. The heliosheath, the helipore, and the termination shock are the areas of interest. The solar wind, a stream of charged particles that blows outward from the sun in all directions, shapes the heliosphere. This solar wind carries the sun's magnetic field lines closer to the sun, moving supersonically, faster than sound in that atmosphere. It finally comes into contact with the interstellar plasma as it travels away, slowing down and creating the termination shock. The heliosheath, a tumultuous area where the solar wind is slowed, compressed, and heated, lies beyond that. Last but not least is the helipore, which is frequently referred to as the border between interstellar space and the sun's domain, but the relationship is more intricate than a straightforward demarcation. Scientists argued over the precise boundary of the heliosphere for many years. It was known to reach well beyond Pluto's orbit. However, it was unclear how far. Instruments on board the Voyagers were able to identify variations in the magnetic field and particle environment. These measurements began to show changes in the flow of charged particles as they departed from the sun, indicating that the spacecraft was getting closer to the boundary. However, it's not an abruptly visible barrier that you can capture on camera. It's more about interpreting variations in solar wind speed, magnetic field patterns, and cosmic ray direction. Voyager may be the first spacecraft to enter interstellar space, scientists realized. The statistics indicated that it had experienced a termination shock by the late 2000s. Based on variations in plasma density measurements the spacecraft took in 2012, Voyager 1's entry into interstellar space would be formally announced in 2013. In 2018, Voyager 2 entered interstellar space via an alternative path. These changes were landmarks in space travel since they were the first instances in which man-made objects have left the shield of the solar wind. Our knowledge of the interactions between the sun and the galaxy is already being rewritten by the discoveries made in this boundary zone. The level of turbulence discovered by both spacecraft was unexpected, with cosmic rays and plasma waves swirling in unexpected directions. Additionally, they discovered that the heliosphere's shape might be more asymmetrical than the tidy comet shape, suggested by some early models. The new findings are helping scientists better understand the shape of the heliosphere and how it affects cosmic ray penetration into the inner solar system. The data on particle fluxes, plasma density, and magnetic fields tell an intriguing story, despite the fact that we cannot see this barrier in the same way that we can see a planet or moon. They demonstrate how high-energy particles from pulsars, supernovas, and innumerable other cosmic events continuously bombard the solar system, which is a component of the galaxy's dynamic environment. Maybe not as much as previously thought, but some. Of that barrage is moderated by the sun's own magnetic field and outflow, the helipause and the termination shock. When the solar wind encounters the interstellar medium, it slows from supersonic to subsonic speeds, a phenomenon known as the termination shock. For both Voyagers, crossing this area was a significant accomplishment. This occurred approximately 94 astronomical units away from the Sun for Voyager 1. However, because the shock itself might vary, pinpointing the precise distance is difficult. Voyager 2 was around 84 astronomical units away from the Sun when it experienced the termination shock. A discrepancy caused in part by changes in the interstellar environment and solar activity. Each spacecraft learned something new about the energy exchange in this border zone by passing through the termination shock. Charged particles can accelerate along magnetic field lines or bounce back toward the inner solar system. This region is more turbulent than anticipated, with shocks and waves that can accelerate particles to high energy, according to data from Voyager's cosmic ray detector and plasma equipment. Some of the cosmic rays found close to Earth might be explained by such acceleration processes. Each Voyager entered the heliosheath after surviving the termination shock. The solar wind's chaotic flow collides violently with interstellar plasma in this region. The heliosheath was supposed to be a more seamless transition, but both spacecraft discovered greater chaos. Although the interstellar plasma density starts to increase and the spacecraft comes into contact with more high-energy cosmic rays from outside the heliosphere, this area is still within the Sun's magnetic pull. The spacecraft eventually came into the helipore, the last threshold where the interstellar medium essentially overwhelms the effects of the solar winds. A sharp change in particle density and a shift in magnetic field line orientation were used to identify the crossing for Voyager 1. Scientists were informed that the spacecraft had left the heliosphere by increasing discrepancies in the cosmic rays it monitored. Later, Voyager 2 crossed and verified a barrier as well. However, there were enough differences to demonstrate that the helipore is not a tidy, stable shell. It probably stretches and contracts in response to interstellar medium pressure and solar activity. Thanks for watching another episode. Please like and subscribe for similar content.